Isomers are compounds that have the same molecular formula but different connections or different arrangements. These isomers can be broadly categorized as structural isomers and stereoisomers. Structural isomers are isomers that have different connections. For example, for the formula C3H7Cl, we can draw two different structures. One, 2-methylpropane, in which the chlorine is connected to the middle carbon. The second, 1-methylpropane, where the chlorine is connected to the end carbon. So the connections of the chlorine are different, therefore we call these structural isomers. Structural isomers are also called constitutional isomers. The second category of isomers are stereoisomers, where the compounds are connected the same way but arranged differently. This category can be divided into two classes of isomers. One, the conformational isomers. Second, configurational isomers, which we will discuss later. First, let's look at the conformational isomers. And what are conformational isomers? They are compounds that are connected the same way but arranged differently because of the ability of bonds to rotate. Let's take the formula C4H10. One of the structures that we can draw for this formula is long chain butane. 4 carbons with 2 end methyl groups. And now we're going to see how we can represent this molecule in two different ways. One, sawhorse formula, the other one, Newman projections. What we are showing in these two different representations is the different arrangements this butane molecule can take when it rotates around this middle carbon-carbon bond. So in sawhorse formulae, we can draw the two methyl groups, methyl CH2, CH2, CH3. The end methyl groups are on opposite sides. Now this is one conformation that we can draw for this molecule. We call it the anti-sawhorse formula of butane. If we keep rotating around this bond, we're going to come up with a second conformation where the two end methyl groups end up on the same side. And in this arrangement, the two methyl groups are so close to each other, they look like they are overlapped. And this conformation is called the eclipsed sawhorse formula of butane. The same spatial arrangements or conformations of butane can be shown using Newman projection formulas. Rather than using lines to represent the formula, in Newman projections, we are using these two CH2 carbons, one in the front and one at the back. And here are our two end methyl groups. We rotate the molecule the same way around these two CH2 carbons, and let's see what conformations we're going to end up with. When the two methyl groups are on the opposite sides, we call it the anti-Newman projection of butane. Then we keep rotating this methyl around this carbon-carbon bond towards the other methyl group in one direction. We end up with the Gauche-Newman projection, and when the two methyl groups are very close, we call it the eclipsed Newman projection. So let's name these projections now. The first one is called the anti-Newman projection. The second one is Gauche conformation. The last one is the eclipsed conformation. The anti and gauche conformations are commonly called staggered conformations because the groups in these two conformations are somewhat staggered, whereas the last conformation, the groups are all overlapped. If we go back to the sawhorse formulae, just to name these two conformations, the first one is called the anti-sawhorse formula because the two methyl groups are on opposite sides. And the second conformation is called the eclipsed sawhorse formula or eclipsed conformation. Carbon-carbon bond.